All right. Hi, everybody. It's my pleasure to introduce today's Consciousness Club speaker, Matthias Fritsche. I actually know Matthias from the time that we did our masters together at the Donors Institute, which I think was back in 2014. So I remember always being impressed by Matthias's careful and clear thinking already during his masters. And after his masters, he went on to do a PhD and a short postdoc with Professor Floris de Lange, also at the Donors Institute. And since 2021, Matthias is a postdoctoral fellow at the Department of Physiology, Anatomy, and Genetics at Oxford University with Professor Armin Luck, where he changed from working with humans to now also working with mice. And he uses a combination of psychophysics, computational modeling, and neuroimaging to study perceptual decision-making. And today he's going to tell us about adaptive history biases in perceptual decisions of mice and humans. Matthias, take it away.
Thank you very much for the nice introduction, and thanks very much for inviting me. It's really a great pleasure to give this talk to you today. So one of the main questions of my research is what enables humans and animals to make successful perceptual decisions? And to demonstrate that this is not trivial, I would like to remind you that our brains receive much less detailed visual information than you may think. For instance, the area of our visual field in which we can see sharp details is roughly the size of our thumbnails when viewed at arm's length. So we constantly shift the area of sharp vision onto different fields of the visual scene, and that causes constant shifts to the visual input that enter our brain. Right, and on top of this, we often have to deal with degraded visual input. For instance, imagine driving your car on a rainy day or during nighttime when important details are difficult to see. And visual input can also be ambiguous. For instance, when you look at this image here, it's unclear whether the cat is walking up or down the stairs. So again, these examples of visual uncertainty or perceptual uncertainty that we face in our everyday life raise the question of how humans and animals can make successful perceptual decisions. And then our brains have probably developed many ways in which to tackle this problem or contribute to this process. But one of them is that our brains can use prior knowledge and context to facilitate perception. So, for instance, consider this street scene here. You will likely see a car and a person in the scene. However, the car and the person are really one and the same shape, merely rotated by 90 degrees and placed in different parts of the image. And it's the context of this street scene and your knowledge about cars and persons that determines how you perceive those shapes. And while this example likely relies on lifelong experiences with the environment and street scenes in particular, previous experiences can also influence perception and perceptual decisions over much shorter timescales. And I would like to give you one example from the laboratory here, which will be the main phenomenon that I will address in this talk. Right. So in this experiment, humans see a cloud of moving dots, and they have to decide whether the dots are coherently moving upwards or downwards on the screen. And they do this for many trials in sequence. And usually what we do in these laboratory experiments is to carefully randomize the sequence of stimuli such that each stimulus is independent of the previous stimuli. And you can see an example sequence here, where sometimes dots are clearly moving upwards, sometimes they're clearly moving downwards, and often the motion is ambiguous. But every trial is independent of the previous trial. What we typically see is that human observers, like this participant here, give very repetitive responses. So this person responds with upwards motion a couple of trials in a row and then switches to reporting downward motion. And when carefully analyzing this across trials and across observers, we often see that perceptual decisions are not only influenced by the current stimulus, but people are also, they're tending to repeat the decisions that they've made on the most recent trials. And that is not only limited to motion stimuli. You can find this virtually for any visual feature that you can come up with. And that there's like an extensive literature on these choice history biases. And it also doesn't only happen in humans. So monkeys doing a motion discrimination task, they show similar choice repetition biases. Rats that do olfactory discrimination tasks to show this tendency to repeat their decision of the previous trial. And mice that are engaged in a visual contrast discrimination task also tend to repeat previous choices. So this is really a phenomenon that occurs for many different perceptual features, but also across different sensory modalities and across species. And naturally, we researchers have then asked, like why do these choice history biases occur? Are they good for anything? And in these laboratory settings, it's clear that they're not good because when you carefully randomize the stimulus sequence, then any choice the history dependency that you exhibit actually makes you worse on the task because you're relying on unpredictive previous information. However, researchers have argued that when you go into the real world, the situation is different, and our world usually does not change over short timescales. So at the moment when you're sitting at your desk and you're looking at your computer, it's quite sensible to expect that your computer or desk, they don't suddenly disappear. So when you face perceptual uncertainty, you might leverage this stability of your environment and incorporate it into your decisions in order to make better decisions under uncertainty. And that has been like one of the most prominent explanations of this choice history biases in the recent literature. However, I think it's also clear that you can come up with many examples where our world is not very stable. So when you get up from your desk and you go outside for a run, your visual environment would change much more rapidly than was currently the case. And there are also many examples in which our world changes dynamically, albeit predictably. For instance, when you see a traffic light switching from green to yellow, you can safely assume that it would turn red in the next moment rather than stay yellow forever. Right. So it's clear that our environment exhibits a multitude of temporal regularities and it's not always stable. And in the research that I will present you today, I've looked into whether observers can adapt their choice history biases to different temporal regularities, which would provide more evidence that these choice history biases actually originate or reflect processes that try to facilitate perceptual decisions based on temporal irregularities. Right, so here's a quick visual outline of the talk. So first I will show you some mouse psychophysics data that we collected. And I show you that mice can indeed adapt their visual decision-making biases to different temporal regularities. Although we see some quite surprising features in their behavior that were quite puzzling. And then I present you a computational model which accounts for this behavior in mice, and particularly the adaptation to different regularities, and also provides some nice explanations for these puzzling observations that we made. And then I go on to show you some dopamine recordings from the dorsal striatum in mice while they're doing this decision-making task. And we will look at these dopamine signals through the lens of this model. We will look into the neural substrates of these computations. And then finally, I will show you some human data in very similar tasks to what we did in the mice. And while it's clear that the mice are not miniature humans, I hope that I will be able to convince you that we see some really nice similarities between the species, which might help us to generalize some of these findings across different species. Right, and by the way, if you have any clarification questions during the talk, then yeah, please just interrupt me and ask. So first, the mouse behavior experiment. So what we did with mice is we trained them in a visual contrast discrimination task. So we head fixed them in front of a small iPad screen, and they have a little wheel beneath their forepaws. And what we do is we present visual grating stimuli either on the right side or on the left side of the screen. And the task of the mouse is to report the location of the stimulus by moving this wheel, thereby bringing the stimulus to the center of the screen. And when they successfully do this, they get a water reward. And when they move the wheel into the wrong direction, then the stimulus moves outside, and it's an error trial, and they don't get rewarded. Right, so here's a video of a mouse that's doing the task. You can see in the bottom what the mouse sees on the screen, and that's a really expert mouse that's hardly making any mistakes, and is quite vigorously doing the task. And then when we train these mice, we first start with very easy stimuli, high contrast, they're very, very easy to see. It still takes them quite some time to figure out how to turn the wheel, to move it to the center. But then when they become expert, we introduce, in addition to these high contrast stimuli, we introduce lower contrast stimuli, which increase the perceptual difficulty of the task. And then our manipulations are this. So on some days, we show them completely randomized stimulus sequences. So that's kind of like the experiments that I showed you on the previous slide, where on every trial, the stimulus is determined randomly, and there's no predictability in this task. And then on other days, we expose them to what we call a repeating environment, where there's an 80% probability that the stimulus on the current trial will be in the same location as the stimulus in the previous trial. And that generates sequences like this, where you have these local repetitions of the stimulus location. And then finally, we introduce an alternating environment where stimuli are likely to switch locations from one trial to the next, creating these alternating sequences. And we randomly interleave these different regularities or different environments across days. And first, I show you that the mice really become expert in this task. So here's the data from 10 mice, where on the x-axis, I show you the current contrast of the visual stimulus. So a negative value means that's a stimulus on the left-hand side with 100% contrast. And then +1 means a stimulus on the right with 100% contrast. And you can see that when the stimulus is on the right, they almost always report that the stimulus is on the right. And when the stimulus is on the left, they almost always say that it's on the left. And then when the contrast decreases, the responses become more variable, reflecting the perceptual uncertainty that the mice have in these situations. And then to look at how they are influenced by their recent choice history, I split this psychometric curve into sets of trials where the previous rewarded choice was to the right-hand side or to the left-hand side. And I look at how their current response probability is impacted by that. And you can see that in the neutral environment, the purple data points are just slightly shifted above the green data points, meaning that when the previous choice was to the right, the mouse is more likely to respond right again compared to when it was on the left. And that's more clearly seen when looking at the difference between these psychometric curves. So that's just really taking the difference between each data point. And now a positive difference means they are more likely to repeat their previous choice. And one feature that you can already see here a bit is that this bias is increased when the current contrast is low. So when the current perceptual uncertainty is high, then mice show stronger repetition biases. When we look at the repeating environment, we see that their repetition bias is much increased. So they're in the repeating environment, they're more likely to repeat their previous decision. And again, mostly so when the current contrast is low. In the alternating environment, the mice tend to start to alternate away from their previous decision. And so this is some good first evidence that they actually do adjust their choice behavior to these different temporal regularities. And in fact, when you look at the choice accuracy across these different environments, you see that the accuracy is increased in the alternating and repeating environment over the neutral environment, which means that they're performing better in these environments with this regularity because they are adjusting their choice history biases to that regularity. Right. So that's some first evidence that they are adapting their choice history biases. But we wanted to look into this in more detail. And for this, we, in line with previous studies, we use a logistic regression model to explain the choices of the mouse based on the current stimulus contrast. So that's basically the task that they have to do, respond to the current contrast. But then also by past correct choices and past incorrect choices to investigate how the decisions rely on these previous decisions. Right. So first, to get this out of the way, when we look at the influence of the current stimulus contrast, the coefficients are highly similar across the environment, meaning that they don't become more or less sensitive to the current visual input across these different manipulations. And then we look at how they rely on these past choices. And what we see is the following. So here on the x-axis, you see the n-back trial. So where 1 means the previous trial, second previous trial, third previous trial, and so on. And on the y-axis, you see the choice weight, meaning like how much is this choice influencing, this past choice influencing the current choice. And I've already shown you that in the neutral environment, mice are slightly repeating their previous decision. Right? So now what was surprising to us is that we found that actually they're more likely to repeat their 2-back decision than they are than they tend to repeat their 1-back decision, right? And that was quite odd to see for us. We would have expected to see the monotonically decaying choice weight, but we see this 1 to 2-back increase. And from there on, the choice weights do indeed monotonically decrease, as you would expect. All right, so this is the first kind of surprising feature we see in the mice, which I will explain later on with the model. But yeah, keep this in mind that this was this kind of like curious behavior. Then I've already shown you this, that the mice tend to repeat their 1-back decision more than in the repeating environment than in the neutral environment. And what was again surprising to us is that when we look at the influence of decisions further back, they're almost exactly the same as in the neutral environment. And in the alternating environment, mice tend to alternate their previous choice. Again, I've shown you this on the previous slide, but you might have guessed it, that for the 2 to 7-back decisions, they weigh this almost identically across the environment. Right, so we do get a clear adaptation in the 1-back choice weight. So they adjust their reliance on their previous decision to the environment. And that's very consistent across mice. But they also show this dependency on past decisions that is quite similar across these different environments. And yeah, basically just implies a choice repetition from the 2 to 7 back trials. One thing that I looked at next is how fast they are actually adapting these previous decisions to these regularities. You could imagine, like, you put the mice into a alternating environment, and they would very quickly pick this up and start alternating. Or alternatively, they might develop these biases over very long time frames. And to look at this, I capitalized on the fact that we often ran these sessions across days in this blocked manner, where I show, for instance, 3 alternating environments across 3 days, and then switch to neutral for 2 days, and then switch back to repeating, neutral, alternating, and so on. Right? And then I asked, how does this alternation weight develop over prolonged exposure to these regularities? And what we find is that while initially the mice don't alternate very strongly, as they get more experiences across days, they alternate more and more. So actually, this alternation bias develops over many hundreds of trials across several days, where in the end, all of the mice alternate. But it really takes a long time for them to develop this bias. And you see basically the same thing when you look at the behavior in the repeating environment, where they start out with relatively neutral weights and then start to repeat more and more across days. Right, so there was the kind of second surprising finding, is that even though these adaptations to these environments, they are in a way quite local, like only affecting the weighting of the one back decision, the tendency to, or the reliance across these different environments develops very, very slowly across days. And another way to look at this is to look at how mice are behaving, or how they are making decisions in a neutral environment, where the stimulus sequence is completely random, after they come from a previous day where stimuli alternated or repeated. And what we see here is that when you put a mouse in a neutral environment after an alternating day, they would continue to strongly alternate their decisions compared to when they come from a repeating day where they repeat their previous decisions. And that's quite remarkable, I think, because here the decisions are to statistically identical sequences, both completely random, but the only difference is what they experienced in the previous day. Right, and again, this is highly consistent across mice, and you see that in the raw behavior, that when the current stimulus contrast is low, they strongly repeat when they, on the previous day, experienced a repeating sequence, and they alternate when they experienced an alternating sequence. Right, so these choice biases, these adaptive choice biases to these different regularities, they develop very slowly and carry over across sessions. And that brings me to the interim summary of this behavioral part. What I would like to highlight is that there's quite a fast repetition bias, where the local choice history influences current decisions, and that effect decays over about 7 trials. Right? But then there's also a very slow acquisition of the one back, or slow adaptation of this one back choice biases to these temporal regularities. And furthermore, that's a highly local effect, where the regularities really only affect how mice weigh their previous decision. And finally, I would like to remind you that we have this strange 1 to 2 back increase in the neutral environment, where mice more strongly repeat their 2 back choice than their 1 back choice. And after seeing all of this, I was wondering, like, what's the is there an explanation for this adaptation, for this slow adaptation, but also for this strange 1 to 2 back increase in the neutral environment? And I started to explore potential computational models that might explain this. Right. One thing that I would like to mention here as well, and we can maybe go into this in the discussion if you're interested, but we made sure that this 1 to 2 back increase is not due to sensory adaptation, which is usually creating repulsive effects and might explain why this 1 back weight is lower than the 2 back weight. We ran additional experiments to test this, and it turns out not to be the case. We also made sure that there's no mixture of decision strategies where sometimes the mice would show a monotonically decaying history kernel, and then sometimes they would, on few tries, they would strongly alternate. And finally, we also find that this 1 to 2 back increase occurs in mice that are completely naive to the manipulation of tempo regularities. So even mice that have never seen repeating or alternating sequences show this tendency to more strongly repeat the 2 rather than the 1 back choice. So that seems to be a more general feature, and it's not due to the specific manipulations that we have done in the task. Right, but next I explored potential computational models that might explain this. And one of these models, which might come a bit as a surprise, that we kind of like looked into this type of model, but one of these models is a reinforcement learning model. And I say it's like maybe kind of a surprise because it's like a perceptual decision-making task. So why would you use a reinforcement learning model? I think one thing that's clear is that the mice are doing this task for reward. So they get try-by-try reward. And that might actually, that reward signal might influence how they are learning, how they are adapting their decisions. And I will explain you in a bit more detail how exactly that might work. So the first step in this model is that it creates what we call a belief state. And that's the belief that the current stimulus is on the left or the right-hand side of the screen. And that is basically determined by the contrast of the stimulus and the sensory noise parameter, which determines the width of this measurement distribution of the sensory sample. So these values take, or this belief state takes values from 0 to 1, where a clear stimulus on the right would have a high belief that the stimulus on the right, so it would be a 1 here, and a 0 for the belief that it's on the left, and vice versa for left stimuli. And the idea is that then the agent combines this belief state about the sensory state of the world with learned values for left and right actions. So these values would tell the agent whether when the belief is that the stimulus is on the left, whether it would be better to take a left action or a right action based on that belief. And what typically happens in this task is that like these values of taking a left action when the stimulus is on the left or taking a right action when the stimulus is on the right, they grow to large values, and these this off diagonal grows to this other diagonal grows to low values because these are the wrong actions given the stimulus. Right? But the model combines then the sensory belief with these values, and it computes an expectation about what reward it expects to receive for taking a left or right action. And it then takes a stochastic action based on this reward expectation. When the expectation is that the left action should give you a higher reward, then it would tend to choose a left action accordingly. And the the important part of the model is that after taking this action, the model gets feedback, and it will compare the reward expectation for the chosen option with that reward. So let's assume that the model thought that the left action should give the higher reward, and it chose the left action. It will then compare this reward expectation to this outcome and compute a reward prediction error, which it will use to update these values in this matrix here. So this learning algorithm basically allows the model to learn this task from scratch without initially knowing which action to take in response to which stimulus. It will, through trial and error, figure out that it should take a left action for a left stimulus and a right action for a right stimulus. And the idea is that basically, while this is like an architecture that allows you to learn the task from scratch, the idea is that even when mice become experts, they might not stop engaging with this learning process. They might continually evaluate which actions to take given the sensory stimuli, right? And when you simulate this model on this perceptual decision-making task in our expert mice, you find that it can explain the psychometric curve very well, and it also accounts for another kind of curious observation, which I have not told you so far, which is that mice are more likely to repeat their previous decision when it was based on a low contrast stimulus compared to a high contrast stimulus. Right? And that's something that the model can recapitulate very well. And to give you an intuitive idea why the model does this, when you show a low contrast stimulus, the belief state will be roughly 50-50 because the agent doesn't know whether the stimulus is on the left or right. So the reward expectation will be relatively low due to this perceptual uncertainty. And when the agent then takes an action and receives a reward for that action, then the prediction error in the model becomes very large because the outcome is much better than the agent expected. And that creates a huge update to these perception choice values here. And that will affect the choices on the next trial. More so than when the contrast is high and the reward expectation is high, then getting the reward is not very surprising. So there won't be strong updates to these values, which then leads to relatively neutral behavior in the next trial. All right, so this reinforcement learning model really provides a nice explanation for this dependence on the previous stimulus contrast. And it also, given the explanation that I've just mentioned, it's clear that it produces choice history biases because the outcome on a given trial will affect these updates of these values, and combining these updated values with new sensory information will bias which actions the mouse prefers to do. And generally, it generates choice repetition biases because it will be rewarded for a correct action, and then the value for that action will increase, and it will tend to repeat the same action in the following. And you can see what the model does in this graph here, which is this monotonically decaying choice history kernel, right? And that's well, at least like 2 to 7 back is maybe not too far off, but it really doesn't recapitulate this 1 to 2 back increase that we see in the mice. And when we look at the alternating condition, it's also clear that this model doesn't really produce strong alternation behavior, and that's just not like possible in this architecture, because in order to do the task successfully, you need to increase the values of the correct actions, and therefore in the next trial you would tend to repeat that same action, and it would be very difficult to switch to the other action which was not rewarded. Only in the repeating environment that model can actually like somewhat recapitulate the empirical pattern that we find. Right? And then when we look at how the model carries over these differences between these environments into a neutral environment on the next day, so to say, we see that the model really produces very similar choice history biases, regardless of whether it was experiencing a repeating or alternating environment on the previous day. And to give you an intuitive explanation why this is the case, is that the learning rate has to be chosen such that you get this rapid decay from 2 to 7 back, right? So that requires like fairly rapid updates to this value matrix. And then when you put the model into a new environment, these rapid updates, they will quickly erase any differences that have accumulated on the previous day to any of these regular environments. Right? So you really don't get these sustained or like long time scale differences in behavior. Right. So we were wondering whether we can make a kind of minimal change to this model in order to make it fit the data. And we figured out that there was actually like a really small addition that you needed to make to make that work, and that is the assumption that the belief state of the model does not only consider the current sensory information, but at the same time it also stores a memory of particularly the previous rewarded action. So in this case, for instance, you might have a situation where the model currently sees a stimulus on the right and has a high belief that the stimulus is on the right, but it also remembers that it has taken a left action on the previous trial. And then the kind of mechanics of the model work in exactly the same way that the model combines this belief state with stored values for left and right actions, but now it's not only learning what action to take based on the current sensory information, but also what current action to take based on the memory of the previous action. And again, it does these updates to this value matrix in exactly the same way as the previous model. Right? And when we look at the predictions of that model, we see that, again, it fits the psychometric curve very well, and it explains this dependence on the previous contrast. But it also explains this 1 to 2 back increase in the choice history weights that we see in the mice. And I will explain you in a moment what the intuitive explanation for this is. I will first show you that it also produces this alternation bias in the alternating environment, while then quickly jumping up to the same level of repetition as in the neutral environment. And similarly, it captures these repetition biases in the repeating environment. And furthermore, when you look at the carryover to neutral sessions, you see that it does carry forward this difference in 1 back choice weights when you go from a repeating or alternating environment to a neutral environment. Right. And before I give you intuitive explanations for why this works, I want to really emphasize that this is like quite small model with it has a sensory noise parameter, action or decision noise parameter, learning rates, and memory strength. So it has these 5 parameters, and this parameter set is exactly the same across these 3 different environments. So it's not that we are kind of tweaking like the parameters to fit each individual environment, but we find one common set of learning rates and memory strength and so on to explain the behavior across all 3. And I think that's quite remarkable, because it would basically, what it means is that the agent does not really adapt the learning, like the learning rules to different environments. It's just the interaction of this incoming visual input with like the learning mechanics that the model has that generates this different behavior. Right, and now, yeah, I want to give you like this explanation why this 1 to 2 back increase occurs in this neutral environment here. And for this, it's important to realize that while, as in the previous model, this model will grow the perception choice values along this diagonal, making left actions more valuable when the stimulus is on the left, and right actions more valuable when the stimulus is on the right. This part of the model, which learns what actions to do based on the previous memory, that can develop very flexibly. So that part can learn to take a left action based on a previous left memory, but it can also learn to take a left action based on a previous right memory, right? And that is essentially what allows the model to develop these different biases to these different regularities. But what will happen in the neutral environment is that this part of the model will push the model to repeat previous actions. But as I mentioned in the introduction, in a neutral environment, that's actually not good, because you should be actually history independent. Repeating your actions will actually only make your decisions worse. And the model will realize this by basically overestimating the reward that it will get based on this perceptual part of the model. And when it gets the outcome, it will realize that it overestimated, and it will adjust the memory values to improve this reward prediction. And it will basically, in a neutral environment, therefore weigh down the 1 back choice weight to repeat less, and therefore become better in the task in the neutral environment. Right, so this 1 to 2 back increase might actually be like a normative adjustment that is enabled by relying on a memory and basically counteracting the repetition biases that are introduced by this try-by-try updating based on perception. And another intuition for why this carryover persists when you go to the neutral environment, when you go to a neutral environment, is that while the learning rates are quite fairly high and produce this 1 to 7 back decrease over quite short timescales, the memory is estimated to be quite low. And because we're updating these values weighted by the belief that you are actually in this particular state and the memory is weak, these updates to this memory part will be quite small. And therefore, these perceptual values, they will change much more rapidly than these memory values, just because the perceptual signal is so much stronger than the memory signal. And that creates this long-term development of these choice biases, right? But what I really want to to take home from this is that we can produce these adaptations across these environments with just a single set of parameters in this relatively simple reinforcement learning model, right? And the different input regularities, they interact differently with the learning rules in the model to produce this different behavior. And these observations, they're not trivially produced by tweaking some parameters in the model, because there's no like separate parameter for adjusting this decay and adjusting the strength of these biases. They are all really like basically all of these phenomena here, they depend on an interaction of parameters. Like you get this decay by setting a certain learning rate and a certain memory strength for like, yeah, getting this decay and these adjustments by setting these two parameters, but that will also determine how much carryover you get and how much you get this contrast-dependent updating here. So it's really like these parameters, they are quite constrained by this data. Right. So having this model, we were now wondering, can we actually find like the neural substrate of these computations? And because we have this value model or the reinforcement learning model, it was quite natural to go to the dopamine system, which has been strongly implied in signaling reward predictions and reward prediction errors in value-based decision-making tasks. So what we did in the task is we recorded dopamine from the dorsal striatum in mice while they were doing this task. And here's a video of a mouse doing this task while showing simultaneously the dopamine signals that we recorded. And you can see that when there's the stimulus coming onto the screen, there's a large increase in dopamine. And then when the reward comes, there's like a second bump in the dopamine signal. Right. So when we look at stimulus-aligned dopamine signals, we see strongly contrast-dependent signals here that with increasing contrast, dopamine release gets stronger and stronger. And that's in line with this reward prediction here in the model, where when you increase the belief state, basically you increase the sensory evidence, you get stronger reward predictions. And then at the time of reward, you get kind of the opposite pattern, where you see that after the reward is delivered, you get a large increase when the stimulus contrast was low, and you get a relatively small increase when the stimulus contrast was high. And that's consistent with a reward prediction error, where for the low contrast stimuli, the uncertainty of getting the reward was relatively high, and then you get a big surprise when you get the reward. Whereas when you had a high contrast stimulus, you were quite certain that the reward would come, and then you only get a small increase in dopamine. I focus on the stimulus signals here because for the reward signals, you always have this overlap between the stimulus signals and the reward signals, so they are quite tricky to analyze. But here I focus on these stimulus signals instead. And one question is, how do they relate to behavior? And one thing we find very consistently is that when you look at behavior on trials with strong or weak dopamine signals, it really reflects the choice accuracy of the mouse. So when you have strong dopamine signals, the mouse is more accurate given a same level of contrast compared to when you have weak dopamine signals. And that's another way of just quantifying this, the increase in choice accuracy with dopamine while controlling for the bottom-up stimulus contrast. And that's an interesting situation because this is quite consistent with the definition of statistical decision confidence, where a confidence signal should scale with the choice accuracy, where high confidence leads to high accuracy choices and lower confidence should lead to low accuracy choices. So here we can take this trial by trial dopamine fluctuations, and we can ask how these fluctuations on the previous trial impact the choice repetition probability of the mouse on the current trial. Right. So what I did here is to condition my data on the magnitude of the dopamine response on the previous trial when it was rewarded, but crucially at time of the stimulus. And while controlling for the bottom-up stimulus contrast, what I find is that mice are more likely to repeat their previous decision when the previous dopamine response was weak compared to when it was strong. And that is really consistent with this finding that we see when we condition on stimulus contrast, indicating that when the decision uncertainty is high, either because the contrast is low or because of like internal fluctuations reflected in a low dopamine signal, that's the cases where the mouse makes the strongest updates to its decision biases. Right. So what I want to take what I want you to take home is that dopamine in the dorsolateral striatum is consistent with reward predictions and reward prediction errors. And it reflects try-by-try fluctuations in choice accuracy, which gives us a window into the decision uncertainty of the mouse. And thereby we're able to confirm that they're indeed repeating their choices, their previous choices made with low confidence. Right. But crucially, we also wanted to know, is the dopamine signal affected by these memories in the model? Right? And therefore,
Matthias, sorry, I just want to quickly interrupt you that we have about 5 minutes or something left for 5 or 10 minutes. Is that okay in terms of your plan?
Yeah,
Okay,
yeah,
great.
no problem.
Awesome, thank you.
Yeah, so we recorded this dopamine data in random stimulus sequences, and what we leverage here is that in these mice where we did this recordings, we see the same 1 to 2 back increase that we see in the previous behavior experiment, right? Which I explained as a consequence of this memory belief state. So we wondered whether this is reflected in the dopamine signal as well. And when we look at the reward expectation in this model, it's clear that the reward expectation increases with current contrast, but it also depends on the trial history due to this updating that happens in the model. And usually you would expect a higher dopamine response when stimuli repeat compared to when they alternate. That's the putative reason why mice develop this choice repetition biases. Right, but specifically, when we look at the 1 to 2 back trials in the classical like perceptual belief state model or single trial model, we see that reward expectation should be highest when stimuli repeat on the current trial. So the reward expectation should be higher for repetitions than alternations, and that should monotonically decay. Whereas in the memory model, the difference in reward expectation between repetitions and alternations should increase from 1 to 2 back. Right, so this is really like a difference in these models, which is a signature of this either like single trial or multi-trial learning. And when we look at the dopamine response, we see pretty much this pattern of 1 to 2 back increase that we see in this multi-trial belief state model, suggesting that the dopamine signal actually contains an integrated reward prediction, both from current perceptual information, but also based on memory information. Right. So the summary of this is that choice history kernels are well captured by a normative reinforcement learning model that incorporates their belief about the current perceptual stimulus, but also memory of the previous action. And we find that dopamine in the dorsolateral striatum tracks these reward predictions and really nicely conforms to reward predictions and reward prediction errors in this reinforcement learning model, and may represent this integrated reward expectation that is used to update the choice values for the future trials. Right. Finally, I just like 2 minutes, I want to briefly go over some human results. So we have some human data where they also do a perceptual decision-making task, deciding whether stimuli are oriented clockwise or counterclockwise on the screen. So either 45 degrees or 135 degrees, and they receive trial-by-trial feedback about their responses. And this was data that was collected by Magdalena de Rio for like different purposes, but I think it's quite informative in the current context. What we see in the humans is that when we look at their choice history curves, is that they show this history dependency where they are more likely to repeat after a previous correct decision, and they are more likely to alternate after an incorrect decision, which is exactly what the reinforcement learning model would predict. But then I wondered and reanalyzed the data, looking at this previous correct choices, would the humans update more after a low confidence decision or high confidence decision? And what I see is exactly that. So when the previous contrast was low, then humans are more likely to repeat their previous decision. And when the previous contrast was high, then there are almost no choice repetition biases. So this gives us some indication that humans may exhibit similar signatures of confidence-dependent learning, and that they might basically, even though they're expert in the task, they might continue to learn which actions to take based on the sensory stimulus and the reward that they receive. Right, and how they adapt to different regularities. They can definitely adapt to different regularities that has been shown in the past, but whether that can be similarly explained by such a like memory reinforcement learning model that they have presented, I think that's an exciting question for future research. So I think that maybe that's a good time to stop and take questions.
Okay, thank you, Matthias. Let's all unmute and thank Matthias with a round of applause.